Decomposing fractions into partial fractions, part 5. Solving A, B, C, D, etc. In example 2, we are asked to evaluate the integral of negative 9 over x plus 1 squared x minus 2 dx. Before we can evaluate this integral, we need to decompose the fraction into partial fractions. Looking at the denominator of the fraction, we see that x plus 1 is repeated twice and x minus 2 is a unique factor, and therefore this fraction can decompose into 3 parts: a over x plus 1 plus b over x plus 1 squared plus c over x minus 2. Multiplying both sides by the LCD x plus 1 squared x minus 2, we can multiply this out and simplify it to leave us with the equation that negative 9 equals to a x plus 1 x minus 2 plus b x minus 2 plus c x plus 1 squared, and let's call this equation 1. To find the values of a, b, and c, we have two options. Method 1 is where we choose specific values for x, and since we have two linear factors, the choice of x is equal to 2 and x equal negative 1 are obvious choices. So if we let x is equal to 2 and substitute that into equation 1 simplifies to negative 9 equals c times 3 squared, which implies that c is negative 1. If we let x equal to negative 1 and substitute into equation 1, we find that b is equal to 3. We don't have any more linear factors, but we still need to find the value of a. We can now choose any value for x. For example, we can choose x equals 0 in order to find the value of a. Substituting 0 into equation 1 leaves me with negative 9 equals a times negative 2 plus b times negative 2 plus c. But we already know that b is equal to 3 and c is equal to negative 1, and this will imply that a is equal to 1. Method 2 for finding the value of a, b, and c is where we compare the coefficients. For this method, we need to take equation 1 and simplify equation 1 by multiplying out the products. Once we've multiplied out the products, we will regroup the terms and take out x squared and x as common factors and group the constants together, leaving us with negative 9 is equal to a plus c x squared plus negative a plus b plus 2cx plus negative 2a minus 2b plus c. Since the left-hand side of our equation does not have an x squared term or an x term, we can insert the two terms 0x squared plus 0x on the left-hand side. And now we will compare the coefficients of x squared. In other words, 0 is equal to a plus c. Compare the coefficients of the x terms. In other words, 0 is equal to negative a plus b plus 2c. And lastly, comparing the constants, negative 9 is equal to negative 2a minus 2b plus c. Now we need to solve these three equations with three unknowns simultaneously. We could use methods like augmented matrices and Gaussian elimination or Gauss with backward substitution to solve these equations, or we can just use elimination methods. For example, if I look at the equation a plus c is equal to 0, it implies that c is negative a. If I now substitute this into equation 2, it results that b is negative 3c. If I now substitute both these into the third equation, I now only have an equation with c, and 9c equals negative 9, which imply that c is negative 1. And substituting back into the previous two equations, b is equal to 3 and a is equal to 1. Once we have the values of a, b, and c, we can go ahead and evaluate the integral. So, now that we know a is 1, b is 3, and c is negative 1, the integral of negative 9 over x plus 1 squared x minus 2 dx can be rewritten as the integral of 1 over x plus 1 plus 3 over x plus 1 squared plus negative 1 over x minus 2. Our first and our last terms will be very easily integrated as lns, but in order to integrate the middle term, we will have to use the power rule, and therefore we will rewrite that term as 3x plus 1 to the power of negative 2. Now we are ready to integrate, so that will give us ln of absolute x plus 1 plus 3 times x plus 1 to the power of negative 1 over negative 1 minus the ln of absolute x minus 2 plus c, which can be simplified to ln absolute x plus 1 minus 3x plus 1 to the power of negative 1 minus the ln of absolute x minus 2 plus c.